Hello, hope you're all doing well. I'm gonna do another equation of the day by Kave, the wonderful Twitter account. This time I'm gonna do this one from more than a month ago. I just didn't have the time to get to it, but I really did want to make a video about it because I think that, like I said here, there is a lot of learning potential. I wanna take this question to talk about a specific topic that I've thought about recently, both due to this question and because when I'm grading tests, there is some sort of gap in knowledge that I have noticed that is extremely related to this thing, okay, to this type of questions. So I'm not gonna get over and explain how to solve it, more than I'm gonna touch the specifics of how the solution works on a graph. Okay, so first of all, we have two equations of circles. Again, I'm not gonna get into why these are equations of circles. If you don't know that specific material, you can go and learn it on your own. It's very simple, very easy, and you don't even have to, because as long as you accept that this is the equation of a circle, you're gonna understand the rest of the video. Okay, so this first one is the equation of the circle, and the second one is also an equation of a circle after a bit of manipulation, and I already have done the reverse manipulation to get to this equation. This is the second equation. Okay, now we're going to solve it. Isolating y or x and then substituting it in, that doesn't work, because let's try. Okay, let's take this one for example. Let's isolate x. So we're going to move this to the side, so we're going to get x plus 7 squared plus equals 100 minus y plus 4 squared, and then if we take the square root of that, we're gonna get x equals 100 minus y plus 4 squared, all of this in square root, and then minus 7, like this 7 after taking square root, subtracting 7, we're gonna get this for x. If we substitute it in here, we're gonna get a whole lot of mess. Why? Because when I get this squared thing, I'm not gonna get rid of this squared completely, because I have this negative 7 and this negative 4 which are gonna give me together negative 10, and then when opening the brackets, I'm gonna get this squared plus 100, that's a negative 10 squared, times negative 10 times this square root. So I'm gonna get left with the square root. And I'm also gonna have this y squared term here and a negative 2y from opening this. So I'm gonna have a y squared term, a y term, a square root of y term, or even more complicated, because I have the square root of y squared and a square root of y together in this square root, together with constants in the square root and constants outside of the square root. I'm gonna get a whole lot of mess. Like, you can try and solve it like this. Feel free to experiment. It's good to experiment, but also know when to stop. Like, there should be a point where, when you experiment, where you say, oh, okay, so this is why it doesn't work. This is good enough. Wait, it's actually just Control Z everything, so we get rid of this line. Okay. The other thing we can do is just add 75 here, right? And add 75 here, and then we'll have 100 here and here, and I can compare the two. Notice that I'm left with both x and y, and by the way, it also doesn't work to try to get similar terms, because once I have, let's focus on the y's for example. Once I have here and here y squared, but here I'm gonna have negative 2y and here plus 8y, I'm not gonna be able to manipulate it in a way where the y squared terms and the y terms both match each other, either one or the other. Okay, because if I try to add y's, I'm gonna have to add it on the other side too, and if I try to multiply, I'm gonna have to multiply the y squared terms too, etc. Okay, so no, what we are gonna do is really, like I said, add 75 to both sides. So let's just take this here and okay, plus 75, and we're gonna get, instead of this 25, we're gonna get 100. Now we can compare these two. This equals that because 100 equals 100. So let's just take this. I hope I can copy and paste in MS Paint. I need to find a good program for this. Oh, perfect. Now let's open this up. Here I have x squared negative 6x plus 9 8y plus 16. Now the immediate thing you're going to notice is that the x squared and the y squared terms cancel out. Then we're going to group this together, okay? 6x goes here, so we're going to be left with 20x. This together is 65, so I'm gonna get left with 20 here. So this is my equation, or more simplified, y equals negative of 2x plus 2. Okay, so this is our solution, and this seems strange because this is a line. Okay, this is a line. This is not a point. This is not a y coordinate. This is not an x coordinate. This is a line. And this is not good, because why did we get a line? Now it's very easy to just take this y and substitute it in here and then solve, and okay, but let's actually understand why we got a line and not our usual point. Okay, the thing is, let's work on our equations. Usually when you want to try and think about it, you want to try and understand how much this question limits you. Okay, how much the information limits you. So first we have this. Let's read this out, okay? This is a circle with the origin at 3,1 and the radius of the square root of 100 negative 75. Okay, so 5. This one is a circle originating, its origin is at negative 7, negative 4 with a radius of 10. Now what about this when we set them equal to each other? Okay. On the left, we're gonna have a circle whose origin is at 3,1, and on the right we have a circle whose origin is at negative 7, negative 4. Did you notice the difference? Did you notice something that's changed between these two descriptions and these two descriptions? We don't have the radius. Once we set them equal to each other, this vital key of information, this vital piece of information, the 100, is not there anymore. Okay, so what we have is two circles which are equal to each other, and we only know their origin. So they can be anything, because, you know, I can take any radius, and if I take all of the points which are on a circle that originates on negative 7, negative 4, without specifying the radius, if I take all of the points that lie on some circle with this origin, I'm gonna get the entire plane. Same with this circle. Okay, I'm gonna get the entire plane. So that's a problem. But the thing is, the piece of information we do have is that these two are equal to each other. They are both equal to some r squared. I don't know what this r squared is, but they are both equal to each other. They have not the same radius, but the same relationship between the radiuses, the radii. Because if this has the radius of r, this will have the radius of square root of r squared negative 75. Okay, this is going to be the radius of the left hand side. So they do have some sort of relationship. Also, you might think, well, this doesn't even have to be a constant. Like, who said that this is r squared? Who says that this is a constant number? Might as well be some sort of double variable equation, you know, a function f of x and y. How do I know that it's a constant? And in that case, for every point on the plane, f of x and y, let's say I'm taking the points x1 and y1, so f of x1 and y1 is going to be a constant. So for every point on the plane, this is going to be a constant which might change depending on the point, but for every point, this is going to be a constant that's going to be equal to both of them. So if I take them and split them into sets of constants, okay, all of the solutions which are equal to this constant, all of the solutions which equal to this constant, all of the solutions which equals to this constant, and then I take all of these intersections, then I get a line. That's what it means, and let's visualize it on a graph, okay? Here I have these two circles. The top one is the equation of the small circle with the radius of 5, and the second equation is this circle with the radius of 10. But r isn't necessarily 10, right? R can be anything. So if we change r, these circles are gonna grow very, very, very far. Maybe 1000 is a bit much. Let's say 100. So here they are strangers. They have no intersection. If I said it just right, somewhere between 8.9 and 9, it's gonna have one intersection. They're gonna be tangent, and in all other r values, they are gonna be slicing each other. Okay, they are slicing each other at exactly 2 points of intersection. Now, what happens when I take all of these points of intersection, like we said before? It's gonna give me this line, which we found, right? So if we take the points of intersection along every possible solution across a wide range of r's, we're gonna get intersections which all lie on this line. Okay, so what we're actually gonna do, and this is what I'm trying to introduce in the video, is that when we solve equations, we don't solve for x and y, we solve for the intersection. Okay, and usually when you do something in math, you start by the definitions and then work your way with the logic. But here I'm gonna start with the logic, and then by the end we're gonna get to all of the definitions in this intersection solving, because I'm gonna solve everything by intersections. I'm also gonna say that, I mean, when developing something new in math, you might want to start first with just experimenting and then making other rules, because the rules you make up, their only purpose is for you to be comfortable. You know, you develop something so you can use it, so it will have a meaning that works for this specific problem and that helps this problem in a simple way. So in order to create an environment in which everything is gonna arise naturally, we're gonna first explore a bit, and then we're gonna figure out what rules we want to make. So now we have the intersection, and the next step, after finding the intersection between the circles, let's do this already. I'm gonna find the intersection between the line and one of the circles. Now, why is that easier? Why does that why is this progress? Okay, well, first of all, if we go back to MS Paint, we'll see that this immediately, like, I can plug something in instead of y and just be left with only x's. It is the algebraic approach. But also, if I'm looking at it from a graph perspective, a circle is more complex than a line. So if I can take one circle, and actually I'm gonna take this circle and remove it. By this circle, just because I don't like the 75. If I take one circle and remove it and replace it with a line, because the intersections of the circle and this circle are the same intersections of the line and the circle. If I replace it with a line, I'm gonna get a simpler equation. So let's do just that, okay? I'm gonna take this one, and this will be my new system of equations, which we're gonna find the intersection of, like we did up until now. So let's delete all of this, and we'll give this to my equation from this square, like that, and we're gonna move this up, and just like that. Okay. Now let's solve this intersection, this system of equations. And what I'm gonna do now is say, okay, I have this negative 2x plus 2, and from here I'm gonna just substitute stuff in. You know, I know that this expression equals y, and I'm gonna put it in here. Okay, x plus 7 squared plus. Now I have negative 2x plus 2 plus 4. Okay, we can immediately just take this and set it equal to 6. So like this squared, and I'm gonna do one more thing. I'm gonna switch this up, because I have this squared sign here, so I can multiply the insides in negative 1, because again, negative 1 squared is gonna be 1. So equal to anything, so here's that, and I'm gonna change it on my sign. Okay, the intersection of the collection of points where y is negative 2x plus 2, and this collection of points which satisfies like this equation. Now we're gonna solve. So we're gonna get x squared plus 4x squared, so 5x squared. We're gonna get this is only 14x, this is only 6 times 2 minus 4, 14 negative 4, 10x. 7 squared is 4 plus 6 squared is 36, we're gonna get 85, so that's 85. Okay, equals 100. Now, even this seemingly like a single equation exists in the world of intersections, because this is actually the intersection of 5x squared negative 10x plus 85 equals y, where y equals 100. Okay, and I can simplify it even further. I can take it and divide by 5. I'm going to get x squared negative 2x plus 17 equals y, but with y being 20. And the last step is taking 20 away from both sides, right? I have x squared negative 2x. Now, instead of 17, I can call it a negative 3 equals y when y equals 0. Okay? Now, let's graphically look at what we just did, which is exactly the same as, instead of y just having 100 and 20 and 0, like normal equation manipulation. Let's look at it from the lens of manipulation, of intersections. So this is the first equation, okay? 5x squared negative 10x plus 85 equals y, which is 100. I have this intersection. Now I want to simplify it further and divide them both by 5, and then I get a different set of intersections, which is this, and the x values will be the same, right? Now I subtract 20 from both sides, then I'm gonna get this set of intersections. Each of them is more simple than the last, okay? Let's see, I started with 2 circles, then a circle and a line, but a line with a slope that's non-zero, okay, non-zero slope. Then I got to a parabole, which is, a lot simpler than a circle, inarguably simpler, and a line, okay, a line with 0 slope. And then this is just, the same form of, another form of the same thing, just like, again, 0 slope. And then I took it down even further to I still have a parabole, but the line now is the y equals 0 line, which is simpler than the y equals a constant. Why? I mean, look at it from the lens of derivatives, maybe. If I have a parabole and I take the derivative of it, okay, I'm gonna get some sloped line. I take the derivative of that and I get some line with the slope of 0, but it is equal, it does equal to some constant, which is the slope of the previous line. If I take a derivative again, I'm left with this y equals 0 line. This is like the base of all derivatives. This is the simplest function you can have, the y equals 0 function. And now I'm gonna look into the intersections of that, okay? Back to MS Paint. This can be written as x minus 3, x plus 1. This is just, opening trinomial, basically just algebraic manipulation. Something you should know, how to solve quadratics. It's a pretty simple thing, and I urge you to, like, if you have basic algebraic technique and you know how to solve equations, go and learn quadratic equations. This equals y with y equals 0, of course. And now, y equals 0. And now, as we know, if I'm multiplying two things and I'm getting a 0, that means that one of these has to be 0. Okay? So either this is 0 or this is 0, that's just normal quadratic equation. So I'm gonna get, and let's actually take this all just a bit higher. I'm gonna get here x negative 3 equals y, and x plus 1 equals y when y equals 0. A quick editor's note: the reason you can split these two to two different equations and do x minus 3 equals 0 and x plus 1 equals 0 is because, like, through the wall of intersection, how it works. If you have two functions multiplied by each other and I set them equal to 0, the product, I can divide both sides by one of the functions in all of the points where that function's value is non-zero. So, for example, if I divide by x plus 1, I will not be able to divide it in the entire region of x equals -1, because these points are going to be have a value of 0. The function is going to have a value of 0, and that will give me division by 0, which I cannot do. But in all of the other points, in every other point, I can divide by x plus 1. And while it does warp the plane along the x-axis as well as the y-axis, okay, there's some complicated warp here, but it's okay, because what I want to look at is the point where the other function equals 0. Okay, if the other function equals 0, like the value is 0, then no matter what I divide it by, I'm going to get the same thing. So the x value won't change because the point on the plane won't change. So when I divide by x plus 1, I cannot find anymore any other point on the plane apart from the point where y equals 0, which means x -3 equals 0. Okay, I'm talking about the value of the other function, the y of the second function, which is the x equals 3. So I hope it clears everything up on this specific part, which is graphically, it just looks like, this is the same thing, and it looks like this. These two lines when y equals 0. So let's also, we already have the y equals 0 line plotted, which is the blue line here. We're going to get rid of the probability. So now we have the intersections of a sloped line and a constant 0 line. Even simpler. Two circles, circle and a sloped line, a parabola and a sloped line, no, a parabola and a constant line, a parabola and a 0 line, a sloped line and a 0 line. Okay? And with each of these, I'm gonna do one last manipulation. Okay? And I'm gonna say, with one of them, I'm gonna get x equals y with y equals 3, right? Because if this equals 3, then the y equals 0. And I'm gonna get x equals y with y equals -1. And now when I'm gonna look at it in Desmos, this is actually the last intersection. Okay, x equals y with two non-sloped, with two zero sloped lines. Okay, with two constant lines. Now this is the point where I have found best to define the end of the solving. Okay, because at this point, this is the point where you substitute and then you just get a solution, x equals 3. So this intersection, let's define it in this world of intersections. Let's define this form of x equals y, y equals constant as the solution, as the final form. This is the answer. Okay, from here we don't do anything more, but we do our best to simplify more and more and more until we get to this form. And then the intersection is just going to be the x value, which is the y value, which is given. Nice. So now we get the solutions of x equals 3 and x equals -1. Now, one last thing. If I plot x equals 3 and x equals -1, and let's do this in green as well, and I take my two circles, we'll see that they always intersect, like they always touch at the intersection, but they also intersect circles in other places. With the bigger circle and the x equals 3 line specifically, since if I substitute 3 in here, I'm gonna get 10 squared and r is 10, so that's gonna be 10 squared as well. I'm just gonna get left with the y term, so they are tangent, and I'm gonna get one solution. But with the other line, I'm gonna get the intersection and then another point on the first circle and another point on the second circle. Why does that happen? Well, again, degrees of freedom. We have, once we have made this step, okay, looking at the intersections of this circle and this line, we have removed y from the equation. We have been left with only x. We have not regarded y. So we're gonna get some x values, but in order to find the y values, we have to do use this this or this, you know. We have to use some sort of what's the name? We have to use another given, which is the equations. So you will have to substitute both x's into both equations and see when you get correct results in both of them, like the same y result in both of them. Only when there's an overlap do you know that you have solved it and found the right y values. Oh, I'm gonna add something which I, for some reason, didn't think of. You don't even have to look for the intersection of the green line and the circles. You just have to look for the intersection of the green line and the intersection line. Okay, not the circle, because the circle will have unwanted solutions, but this is the line of all intersections regardless of size of the circles, as long as they keep their proportions the same. According to these equations, you know, r and square root of r squared negative 75, and then you just have to find like x equals 3 and y equals negative 2x plus 2, and x equals negative 1 and y equals negative 2x plus 2. This is the intersection that you want. This is the simpler intersection. If you want some more formal proof, some more like getting really into it, these two circles intersect on this line, and since there's and since two lines only intersect at one point, and the green line also intersects the intersection of the circles, then this line and this line must intersect at the intersection of the circles and only there. And the same with this line and this line, then you get the two different intersections, and that's it. So now for the final part of the solution, we're going to substitute the x's and then solve the y's from there. And I'm not going to do it here. I'm going to give it to you as an exercise to solve it through the world of intersections. Okay, through the lens of intersections. Now I know that pretty much all of it was very, very simple stuff. Like, these were very easy equations. I mean, x plus 1 equals y, y equals 0. Give me a break. Just x equals negative 1, let's stop there. But no, we're doing it systematically for an important reason. Not because you cannot solve it, but because we want to figure out a way to think about this and invent some set of rules which will give us our unique solutions and unique correct solutions, but also be consistent with the rest of math. Because up until now you could just substitute stuff in and it will work, and you didn't have to think about it. But now with these circular equations you have to think about it through intersections. Why do I get a line? Okay, what information do I have? What information do I lose? And then why does it yield a line? Why? And because I want to answer that, I'm gonna answer everything through the same method, just so I have consistency, because math is about rules and about consistency and about understanding the rules that you make. Okay, you cannot solve this in one way which doesn't work with all of the rest of math and systems of equations. Okay, why not? Because then you probably made something wrong. If your method only works for this equation, then this method probably just doesn't work, and you've just made something that specifically works here out of pure chance and nothing more. But once you have a defined set of rules, then you can start skipping stuff. But and when you want to develop this set of rules, you have to do it very, very methodically and do everything one by one without skipping any steps. So what are the rules here? Okay, small editor's note, because earlier I didn't quite understand the rules of this intersection world. Okay, when I made the video, my thought wasn't exactly finished, and now I understand it, so I want to make a correction of what I said, and I'm just gonna replace it. So basically these are our rules. When I get an equation, okay, I'm gonna treat the two sides as if they are functions or graphs, but no, specifically functions. Now I can do any manipulation on these functions as long as I do it on both of them, and the manipulations don't affect the variables themselves. That means when I get something like this, I don't know, x squared minus 2x minus 3, and let's say the other one is x negative 3, okay? I can subtract and add stuff from it. I can multiply and divide some from it because it doesn't affect the x, okay? It affects the y. If I look at it from the plane, it's gonna stretch and squeeze the y values. It's gonna maybe shift the graphs up and down, but it's not gonna move them left and right. It's not gonna move any point along the x-axis. It's not gonna change x values. And this is also true for questions like what I've had here, right? I've had this and that, which, no, this is the same thing. This and that, okay? Those two. They have x and y in them. Both of them have x and y. And when I compare these two, I treat them as multivariable functions. Let's call this left hand side and this right hand side. So left hand side equals right hand side. Since they both contain x and y's, then this left hand side is going to be f of x and y. This right hand side, we can call it g of x and y. It's always some sort of function. We'll call them f and g. And when I separate them, when I look at them as different graphs, it's going to be f of x and y equals z, and g of x and y equals z. Maybe that's why these questions are so hard to understand, because in them lies some sort of three-dimensional graph. If I had equations with three variables, it's going to be actually a four-dimensional graph when I compare these two four-dimensional graphs. F of x, y, and z equals w. G of x, y, and z equals w. And I can do anything I want to it as long as I am not changing directly the x or the y. I can add something to both of them because it's on the outside of f of x and y. I can multiply them both by, I know, t, because again it's on the outside of x and y. I cannot multiply the x or the y by t. I cannot change them. And then the final rule I forgot is that the final form is just x equals y and y equals some constant. Now, when I compare this to normal equation solving, okay, because this attempts to be a more general way of solving equations, now you see how these two, this and this, they're the same, okay? In our method, they're interchangeable, like this. Well, when I have x equals y and y equals some constant a, okay, that thing is the same as x equals a. They're interchangeable. That's what it actually means. They are both the same representations of the same thing, like we did up until now. And when I get x equals a, that's the end. And this is why x equals y and y equals a is the final step, okay? This is the key to why this is a solution, because this is the equivalent of x equals a. And I'm also going to use this moment to talk about how important it is to not skip steps, like I just said, okay? To do everything methodically, step by step. Because like you've seen, if I hadn't gone over everything step by step, even when editing the video, to figure out exactly the root of everything, okay, to dig really deep into that and understand why everything works the way it is, then I would have walked away with a wrong understanding of the system that I'm using. And of course, after you finish it, after you're done and you know it well and you understand everything and you have no gaps in knowledge and everything works consistently, then you can start skipping steps. But up until that point, if you have even the slightest doubt, if you understand maybe everything but it's not perfectly simple, that means you should keep on thinking about it until you find the actual correct simple way to look at it. Again, we want to create environments in which this comes up naturally. And this is true for any branch of math, okay? Like, you're gonna solve something and you don't know how to solve it. It's okay to invent your own stuff. It's okay to make stuff up as long as it gives you a satisfying solution that's both consistent, works with the axioms of math, okay? and the axioms that you have defined, and it creates an environment in which the solution comes up naturally, in which it's understandable. That is the point of everything here, okay? Making an environment in which the solution is natural, arrives naturally, where you don't have to look for it. If you're doing a lot of steps and it's very complex and difficult, then you haven't found a good solution. Okay, a good solution is one that is simple, one that is elegant, one that is easy to understand. And that's about it. I hope you learned something new. My point here at the end of the day is not only teach math, it's not at all to teach math, it's to teach how to solve things, how you can solve things yourself. And I hope I did a good job with this. I hope you can take away from this lesson to not only these types of problems, but to other problems in general. I hope you can take some of these ways of thinking, and keep staying curious, keep learning. Bye bye.